So I'll cover the observation side. We'll take a deeper dive. Torsten covered a lot of ground in the opening presentation today. So obviously, a plethora of different data sources, ground-based meteorological observations. You have your soundings that are looking at the atmosphere as a thermodynamic profile. And then you have your satellite observations, which are the most recent sort of assets for data science in this field. You don't have to be a subject matter expert to understand the value of satellite imagery. It's been revolutionary for big data. Obviously, you have the 3 V's of velocity, variety, and volume of data. And it's no surprise to see new entries into this market like Tomorrow.io, which is a very recent company just 3 years ago, taking over from long-term companies like IBM, AccuWeather in this market space. So providing proprietary global weather data. So they're launching their own satellites, commercializing this. They're also built on a vertical of customized high-resolution forecasting models. So not inventing new models, but getting revolutionary data to feed into already existing models and then commercializing it to local customers, all in the large umbrella of weather intelligence software. But the end game is a digital twin for Earth. So where we're all going with all the satellite data is essentially getting snapshots of Earth in different time resolutions and coverages, then feeding that into existing physics-based or data-driven models, which we saw Torsten talk about today. And then eventually you get to a digital twin of Earth that is optimized for climate and weather research. It looks great on paper. The leading organizations are listed above that are working on this. Each one has their own understanding and challenges of this digital twin concept, which is really going to revolutionize the field of weather. And this is just based on the past 2 years of progress in this field. Like I said, everything looks good conceptually, but let's look at some of the physics involved in these processes that we saw a little bit about in Torsten's talk. So, a toy model of a boundary layer and what that looks like in terms of physics. You have your soil components, you have your subsurface, which is not even shown here, and then you have feedbacks to your boundary layer, your vegetation, cloud cover, solar radiation, how that all comes into play. Looks good. Then you have to look at feedbacks between all these different processes, different scales of both time and space. So radiative feedbacks, I won't go, each one of these is actually multiple PhD theses, so I won't go into these in detail. So you could actually look into this, and there's also research that's been going at MIT on soil moisture precipitation feedback. So how does the wet soil in your ground surface layer impact your precipitation field? And that's been going on for the past 2 decades, and we're still not sure how that relationship looks like. So then, of course, so this is how eventually it'll look like if you want to capture everything in an ideal scenario. And you're asking a model, you're trying to basically capture this in a physics-based model. So you can imagine the amount of computation involved, and now we're trying to throw all that away and look at AI-informed decision making. So I'll look again at the scales of atmospheric motion. So traditional global climate models will look at things like mesoscale systems, which is a cluster of clouds, storm scale. And then, these are the most used global models to date in no particular order, so I don't get anybody angry. So the ECMWF, which we heard about today, they have what's called the integrated forecasting system. I would say this is the most widely used global model to date. Their ERA 5 reanalysis product particularly. You have ICON, which is the German model, the GFS, which is the US-based model, and of course a couple of others. In the recent 2 to 3 years, we saw that again today. Google released their own data-based, data-driven model. Huawei, Pangu Weather, who I just met with last week, trying to figure out what that looks like for the UAE, NVIDIA's ForecastNet, and then ECMWF themselves, which have been traditionally running physics-based model, have what's now called the AI integrated forecasting system. So a purely data-driven model replacing all the physics. Now, in terms of regional models, so now we want to talk about how do we look at individual clouds, how do we look at cumulus clouds, And better yet, let's start looking at things like turbulence. So actually tracking individual particles within a cloud. And this is the field of cloud microphysics, which again is its own discipline. So I'll talk a little bit about that in the next few slides. But the transition from global to regional, so looking from 25 kilometers down to 1 kilometer, that's a significant jump in terms of the physics involved. So to date, we have all physics-based models. Again, a number of them that have been fine-tuned over the US, for example. You have the high-resolution rapid refresh. You have the Central Europe Super HD, and then the Swiss model, which we saw also in Torsten's talk. So these are the most established regional models. So data-driven models per se have not really been tested to the degree of operational impact yet in this sort of kilometer range. But then, just last month, NVIDIA came out with what's called the core diff. What is the core diff? So let's try to decipher what this all means for people who don't understand what happened here. We have what's called an area of interest, which they focused on in Taiwan. They had a certain case there, the typhoon Chanthu. They looked at it in their own their own forecast net. I sort of flip around between Google's GraphCast and then NVIDIA's forecast net. So they ran the global model, 25 kilometer resolution. And then how did they move to 2 kilometers? They had to use the already existing physics-based model over Taiwan, which is the WRF 3D assimilated weather radar data. A lot there. So it's a physics-based model trained on observations. With those two things, they were able to achieve a perfectly looking typhoon at 2 kilometer resolution, which again has a lot of impact, right? In their global model, it's showing that it never hit land. And their 2 kilometer resolution is showing exactly where it's impacting within Taiwan. But the problem is, and we saw that today, is we can't assume that these state-of-the-art models have learned robust generalizable physics. So it's performing well based on the historical data that's been trained on, and all 4 models that I showed before from Huawei, NVIDIA, they're all trained on the ECMWF model, which has its own regional biases, and I'll focus on the Middle East region, particularly if we want to adopt these use cases, what that might look like. And again, they're only designed to minimize the global mean scores for short, medium range forecasts. So really looking at a 1 week and not beyond that. So this is a recent airborne campaign, which is essentially a flying laboratory that I was on during 2019. The aircraft was here for a full summer period, which is actually the highest frequency of convection in the UAE. We flew a total of 23 research flight hours, sampled clouds to get into those processes that I showed within the cloud in terms of cloud microphysics. So this is an interesting snapshot because I wanted to show what the observations showed on this day actually. So this is the skew T diagram, which would show you. So I won't get into too much detail, but the 2 curves, when they meet, that's essentially a very humid atmosphere, and it's an indication of a good conditions for cloud formation. The farther these 2 lines are apart, it's a dry atmosphere and not much cloud formation. So, and the purple curve here, that's the ECMWF ERA 5 model data at the global scale. The black curve is what was measured by the aircraft. So you're seeing here in the 2 red circles, essentially, where the cloud starts and where it ends. And you can see that this is what's called an inversion layer. So, and it's very clear that it separates sort of the dusty environment under you, and it caps sort of the blue skies above you. So once you're above that lever, it's called free convection, and it's where a cloud can grow and precipitate and produce rainfall. So in this particular case, ERA 5 doesn't show any degree of cloud formation, whereas in fact we had this beautiful cloud. And this is not just a single needle in the haystack. This happens almost every day during the summertime in the UAE. ERA 5 fails to resolve these little micro-scale cumulus clouds, which are so important for the UAE. And so why is this happening? It's a clear mismatch in terms of spatial scale of these things. In the tropics, subtropics, where we are, rain doesn't really come from storm cyclones, except on some extreme events. Typically, we have these convective cells, which I'm showing here. It's a single cumulus congestus cloud, which form over the Hajar Mountains. So this is a typical day during the summertime where you have humid air flowing over these mountains bordering Oman and forming. This is just a satellite imagery and imagery from our weather radar showing these clouds echoing on the radar. So we did some statistical analysis to see how frequent do these storms form where they are during the summer period. And it's a very consistent pattern. They have a diurnal factor too, so generally in the afternoon period they form and then propagate inland towards the UAE. So we looked at this long term using different data sets. So we looked at ECMWF, we looked at our own UAE radar network here. We also looked at radiosondes, so those profiles I showed to also look at that. So the findings in a nutshell is in a 20-year period, we're noticing that these events are lasting longer. So these clusters of clouds are lasting longer, which doesn't necessarily mean much in terms of rainfall, right? So you're getting an indication that these are lasting longer. So if we look at satellite imagery, and then we did this comparison to all the ECMWF data, we found it's very difficult to represent these in numerical models. So they're not being accounted for in these global models, especially because they're also not only limited in space, they're also limited in time. So if you're looking at these things, some of them last about 30 minutes, so it's impossible for such global models to capture them here. So when we're training these data-driven models, what are we training them on, right? The cliche is garbage in, garbage out, and I think it's also relevant here. So we heard about precipitation. Obviously, only renewable source of water, but it is ranked #1 in terms of the most important Earth observation for multiple fields. So I won't, and Luca will talk about the hydrology and how that comes in, but essentially the toy model shows that precipitation is the only input to your water balance equation. And whether you do this at a municipality scale or a global scale, you need to get your precipitation right before you start looking at things like storage and use and whatnot. So if we look at the sources of precipitation data, we can group them into 3 broad areas. You have your ground-based rain gauges, which is a point measurement you have, and the more you deploy, the more dense your network is. Then you have satellite remote sensing, which we covered before, or active remote sensing in terms of weather radar. And then you have your model reanalysis products, which again, people like ECMWF, GFS, they all have global precipitation products. And these products are becoming more and more robust. Some of them not only exclusively rely on ground-based, some of them merge. So they merge their satellite acquisitions with ground-based, with models. So they're looking at how they can essentially minimize bias. So if you look at the comparison here, and I'm citing this paper, one of the first papers that came out with the idea of, okay, we have more than 10 different products, which are supposedly global precipitation products, so let's see how they perform at the regional basis. So things look good when you average it for the global scale. You have the peak near the tropics, and then it dries off at the poles. And then looking at regional, so the top figure is your range of precipitation. Wet, very wet regions in the subtropics, dry belt in the Middle East, North Africa region with less than 100 millimeters per year. And then you look at averaging the difference between these products regionally. And you can see some of the highest biases in this region. It's actually over 300%, but they limit the color scale to 50% just to show the relative with the other regions in the world. So, significant bias in this region, despite that we have some of the most sophisticated observation networks here in the UAE, particularly with over 100 stations. So I like to single out the most, again, widely used satellite product, which is GPM. Essentially merges the 12 different satellite acquisitions into one seamless map across the world. It's available at 30-minute resolution at 10 kilometers. Nothing surpasses this at the moment in terms of capabilities. And then if we, this froze here. Okay, so fast forward from that paper in 2004 to this study, which is very recent in 2019, looking at where would we want to use ground-based observations, where would we want to use satellite data, and what the suitability looks like. So again, for most parts of the world, you see these big bulks of color. So for example, in South America, you'd want to use soil moisture-based retrieval. So again, another type of satellite product, but uses soil moisture to back calculate your rainfall. Near the poles, it's pretty unanimous in terms of ground-based observations in yellow. And then again, you look at the Middle East. It's very chaotic. It will vary between 1 kilometer and the other, which product would perform better. So we haven't done much progress in terms of the past 2 decades in terms of what works best for our region here. And it really boils down to observations. So if you look at what is being ingested into these global models, this is what's been ingested in 1992, and this is what's currently still being ingested since 2013. And you see the persistent gap over the Middle East, North Africa region. So most parts of the world is now filled with these high-density surface-based observations, whereas it persists over the MENA region. But it's not necessarily true. So this is what's actually being ingested, but not what's actually available on the ground. So for the UAE itself, the NCM has over 100 automatic weather stations, both offshore and onshore. So it's not reflecting what's exactly in this figure, which is only 2 to 3 stations for the UAE alone. Saudi also has a very, very sophisticated automatic weather station network, which I think is represented in less than 10 stations here. So there's some data sharing issues. There's a lot of other things involved. So I just want to make the point that we're underrepresented in terms of what we actually have. And it's very important for these initiatives like ADIA Lab to highlight these things so we can move forward on these fronts as well. So the question we had when we first started looking at how we can better predict fine-scale rainfall in arid regions like the UAE, and will the incorporation of certain land surface parameters, just because how it's very related to terrain, so most of these clouds obviously form over high terrain in the UAE, so if we incorporate these land surface parameters, will that improve what we currently have? So we started to look at what was the first data-driven multi-source rainfall product from 3 sources: satellite, radar, and as well as land surface parameters. So when you look at how do you figure out precipitation, it boils down to 2, I would say, commonly used methods. So you have your gauge-based calibration. So you look at what's being fed to you by the satellite, you compare that to your point observation, and then you develop a regression to sort of let it to match. And then as you get your satellite imagery, you're correcting it on the go. The more sophisticated method involves blending. So you would blend in different sources of these precipitation products into a neural network, and you'd have it spit out an output that best matches your observed. So the ground truth is here literally the ground observations for rainfall from the rain gauges. So, and then you can even go a step further and look at additional parameters. So the soil moisture precipitation feedback that I mentioned. How do we incorporate soil moisture here? And the idea is that soil moisture is generally a very good background signal for the UAE, because when you don't have rainfall, it's sustained throughout the year, but when you do have rainfall, it's a direct correlation there. So we looked at this back in 2020. We used weather radars. So the weather radars are the dashed lines, that's the coverage, so almost over the entire UAE. We looked at soil moisture from satellites, and then the GPM product, which I spoke about at the 10-kilometer resolution. We used 2 methods. We looked at a simple multi-layer perceptron neural network, and then we did geographically weighted regression to explore sort of the blending of these different data sets. We divided the stations into training and testing stations. We brought everything to the same resolution. You can already see just visually how different these products are in terms of satellite, radar, and gauge observations. So, in general, you get better estimates from satellite at these high terrain elevations over Oman, and then with radar, you get most of the biases in those regions just because of the terrain blockage. So there's a lot of issues with radar, especially when it comes to blockage. Where do you ideally place these radars to avoid most of the blockage from the signal that's going up to the cloud? And if you look at, again, the soil moisture, how that comes into play, this is a period of 5 years of daily soil moisture data in black. That's the black signal, and that's actually retrieved from a satellite. And then the top curve, which is the blue curve, is from the rain gauge at this particular location. So you can see a perfectly correlated signal there that actually can be used in the sense that once the satellite passes over, you have that 30-minute window. If it misses that rainfall event, it can be captured from the soil moisture. So that's revolutionary because you're able to basically feed in anything that was missed from the satellite. So this is just how we did sort of the resampling and the grid point matching. I'll skip the math here. Luca, I'll save that for Luca's work. And then this is just the geographically weighted regression. So essentially it's distributed in time and space. These are the inputs: radar, satellite, soil moisture, elevation, and your bias, of course. And the outcome would be your corrected precipitation. The neural net is a little bit more complicated. We have to do some cross-validation, dividing, training, testing gauges. So a very simple trial, and this was before really AI was becoming really mainstream in the field of climate science. This was back in 2019 we first started this work, which then Luca took to the next step, and we'll see in his talk in terms of deep learning and using more advanced architecture. So what we essentially found is that the neural net is able to not only outperform traditional regression models, but is also able to remove these anomalies in the satellite itself. So there are, admittedly from the developers themselves, there's some issues, particularly for coastal regions, where there's these artificial signals in rainfall. So no rainfall whatsoever, but something is spat out by the Kalman filter on those satellite processing algorithms. So in this case, you're seeing in red a totally artificial signal in GPM, and then nothing in the top figure, which is the actual observed rainfall. So what does the neural net do in the third layer here? The neural net simply suppresses that spike, whereas in the geographically weighted regression, it's still there, but at a little bit higher magnitude. We looked at this for the past 5 years, tweaked and got a lot of lessons learned. We looked at different seasons. So for summer, how does it perform for summer, and then winter seasons? And essentially, if the Taylor diagram is obviously whatever closest Euclidean distance is to the gauge, that means it's outperforming. In all these cases, the neural network was closer to our observed rainfall. So a very robust model, very computationally inexpensive, can be scaled for other regions in the Middle East to get some accurate precipitation data. And then we sort of did some sensitivity analysis to look at what's happening when we exclude each of these variables one at a time. So we would exclude the satellite rainfall, rerun and train and test. We would exclude the soil moisture, rerun and train, radar, and then elevation. So each time we wanted to see how much, essentially, how much of the variance is being used in each time in these iterations. So it's interesting to see that in the soil moisture case, you're getting the largest difference in RMSE between the neural network and the geographically weighted regression. So your neural net outperforms particularly for that variable in the sense that it's able to understand the relationship between soil moisture and precipitation just from the data itself. So that was a good finding in this work. Fast forward, we are now 1 month out exactly on the point from the big announcement between G42 and NVIDIA on developing what's called a Abu Dhabi climate lab, and it really sets a precedent for the region here to start looking at these things. So we saw the NVIDIA case study over Taiwan, and it's going to be a very interesting time to be looking at these things for the region here. Nobody else is, so far as I know, is looking at these things, and we are in the ideal place and time in the sense that we have all the observations, like I said, the most sophisticated weather radar networks in the Middle East, the most dense observation network. So we own a lot of data. That's why I think NVIDIA is so interested in this collaboration. But then again, soil moisture, we still lack in that. So NCM itself doesn't monitor soil moisture. I don't think any other organization in the UAE does it on a routine level, except maybe municipalities or in certain limited locations. So we do need to look at collecting soil moisture observations. It's very important for this region here. You might think it's a dry environment. Why do you want to look at soil moisture? But it has so much impact at these individual events that we're looking at in terms of rainfall. We also need to look at more advanced instrumentation. So your typical weather radars would only detect clouds once they start precipitating, whereas other types of cloud-specific radars and LiDARs would detect more of the atmosphere on a routine basis. So looking at these advanced instrumentation would help feed into the bigger picture. And then, the region here, Saudi recently announced their own cloud seeding program. So once you want to do climate intervention, you need to understand your current climate scenario, and then based on that, do climate intervention. If you don't understand your current nature, you can't understand what kind of intervention techniques you have. So that will pave the way for the next step, which is already being published by a lot of universities and basic applied research efforts on cloud microphysics. So how do I start now, take it to the downstream of the micro scale of what's happening in a cloud, looking at all these individual processes of collision coalescence, your liquid phase of a cloud, how that interacts with the freezing part of a cloud. So basically tracking individual hydrometeors. With that, I think I'll come to the end and happy to take questions.
Perfectly on time. Thank you, Dr. Wehbe. Any questions?
Oh, my name is Muhammad Ahmed. I'm a 13-year-old. I'm 14. Earlier, you mentioned about the creation of a digital twin of Earth. Has it been created yet, and how accurate is it?
Great question. It has been created. That's the short answer, that yes, there are 3 to 4 digital twins of Earth out there already. Your next question was, how does it perform? In terms of, so it's basically your Earth, but customized for what's happening in terms of weather. So it's able to tell you where the clouds are forming at a very large scale. But if we want to look at, hey, is it cloudy in the UAE at the moment? That's where they suffer. So that's why we're trying to basically take it to the next level, get higher resolution, and look at individual areas even within the UAE.
Any other questions? Okay.
Youssef, regarding the observations in the area, you showed that actually both the Saudi and the UAE have several stations that are not reporting in the public data. But what is the outlook in the future for making that data available and share with research that has been, one of the pillars for research in the US, for example? Well, everything's pretty much public.
Mm-hmm. Yeah, it's definitely a paradigm shift. I think it's starting to happen, Luca. But there's some, I think, political decisions need to happen as well. Data privacy is obviously an issue here, and it's becoming more and more evident that we need to start talking about these things. So, in hindsight, had the UAE or the GCC region shared this data with ECMWF, for example, for the past 10 years, we wouldn't be maybe seeing these biases at the moment. So, I think, and then. Will other people use that to the UAE's advantage or not? So there's a lot of talk about these things, and these conversations are already happening. So with the work with NVIDIA now, that's, I think, transformative and will open the gate for other, I think Saudi is already interested in looking at this too. So.